So now Jayashree will be giving an introduction about today's speaker. And again, thanks Mr. Sivanidhi sir for accepting our invitation for today's FTP. So now Jenny can start.
Um, a very happy evening to everyone presented for secondary faculty development program. Today it is my honor to introduce our distinguished speaker, Mr. Shivanidhi sir over here, who brings over 4 years of specialized experience in medical device quality assurance and agile project delivery. Mr. Shivanidhi sir is currently working as an on-site Scrum Master in medical and life sciences domain at Capgemini, Gujarat. In this role, he leads cross-functional teams, manages project workflows, and ensures effective collaboration to deliver high-quality solutions for healthcare clients. Earlier in his career, he has developed expertise working with Class 2 medical devices, test cases, and executing manual testing to meet strict quality standards. His work demonstrates a strong ability to translate complex technical requirements into structural strategies and enhancing products' reliability, compliance, and efficiency. Beyond his professional achievements, he is appreciated for his commitment to mentoring and knowledge sharing, guiding team members, and supporting continuous improvement in fast-paced environments. Today, he joins us to share his insights on advancements in biomedical engineering, healthcare innovation, and research data automation, a global perspective highlighting how agile methodologies and robust QA products drive innovation. Sir, it is a pleasure to have you here, sir. We welcome you.
Yep, thank you so much, Jayashree. And yeah, hi everyone. So, me Shivanidhi. So just call me Shivanidhi only. Don't call me sir. Okay, I'm just younger than you all. So call me Shivanidhi only. Yeah, I think without further delay, we get started. I hope my screen is visible, right?
Yes, sir, your screen is visible.
Sorry, please call me Shivanidhi only.
Okay, it's visible, sir.
Yeah,
Visible.
okay. Yeah, okay. Yeah, so advances in biomedical engineering and the healthcare innovation. So today I'm going to present blood system, so which currently I'm working on. So earlier I was a QA, means quality assurance lead. I was working on this blood system. Currently I have transitioned to Scrum Master, so on-site Scrum Master. So I'm handling two US teams from India. I mean, from Capgemini Gandhinagar, I'm handling two US teams. So I'll just uh, go through like my project, which advance in the blood system. Uh, yeah, so I think so. This I thought I prepared for the students. So I came to know that it's fully for faculty. So you all know, right? So what is blood? What's it? What is main significance? Can anyone? We can have it as a interactive session, so it will be helpful for you all. Am I audible?
Yes, you are
Blood
audible,
is a
sir.
fluid
Yeah.
which is made up of cells, which is
Okay.
also called as fundamental unit of life.
Okay. So what is the main function? So we know that, right? It transports oxygen and nutrients to the body. So it's an important component in our body. So without blood, we can't even like do breathe in, breathe out. For breathe in, breathe out, we require oxygen, and for the body metabolism, we need nutrients. And not only this, so we need some carrier which carries out carbon dioxide and the other waste products. So blood is an important thing, and everybody we actually have 5 to 7 liters of blood, and it is made up of solid and liquid. Solid meaning blood cells, and liquid blood we call it as plasma, right? So it's made up of cells and the plasma. And functions of blood, so like we discussed, so it is a carrier that moves waste from our body, and it helps us to supply oxygen, and it helps us to balance acid and base, and it requires us to supply nutrients. So basically it's a important thing for a human life, right? Does anyone know blood fractionation? So these topics now, see, these are just a introduction, like functions of blood, and the blood is like a introduction. So now this is the important topic in the blood domain. So blood system, if you consider blood domain now, these are the important components or important parameters that you will go through when you comes to innovation or in advancement. Does anyone know what is blood fractionation in your pathology lab or anywhere in your blood center?
Distributions of red blood corpuscles, white blood corpuscles, and other components which is present in the cell. Shivanagi.
Yeah, correct. uh Yes, so it's the process of separating whole blood into a components. We all know the blood is made up of these components: a plasma, a platelet, WBC, and the RBC. Erythrocytes meaning RBC, and leukocytes meaning WBC. So what it will do, blood fractionation is a separating of these components. Plasma, Buffy coat. We call it as Buffy coat. So we can't, with the help of centrifugation, we'll be able to separate it part of Buffy coat only. It's made up of platelets and the WBC. We can't further separate it in, I mean, kind of in the centrifugation, we can't separate it. And the last part is erythrocytes. Here in the test tube, you can see RBC at the bottom. Does anyone know why RBC at the bottom?
So due to it is denser than plasma.
Correct. Correct. Sorry, I'll turn off my camera. Okay. Yeah, because of its dense RBC at the bottom, and Buffy coat will be like kind of foam, so it is a middle part. It's like 1% lesser than, and 55% of plasma. It's a liquid protein, so it is at the top. Okay. Okay. Does anyone know what is hematocrit HCT, or you guys checked in your blood report?
The amount of RBC in the blood.
Correct. So it's a percentage volume. So percentage volume of red blood cell, only RBC count, not any WBC or plasma. It's only purely focus on the HCT. So we should have a definite percentage of RBC in order to donate our blood to anyone. So yeah, why we require HCT? We should use this as a main parameter for diagnose or monitor a number of conditions or diseases that affect proportions of blood made up of RBC. So we will be having more diseases related to RBC, so that will be calculated based on the HCT. If you have seen your blood report now, so this is the main parameter. There will be like two terms: either they will print it as a hematocrit, or they'll print it as a hemoglobin. Yeah, so for evaluation of RBC, either they consider hematocrit or they consider hemoglobin. It helps to make blood transfusion decision. So if you want to give your blood to someone, so they'll consider this as a parameter. And it is normally like for men, the range, definite range is like 45%, and for women it is 40%. So these are like what if the HCT decrease, what it will cause, and what if the HCT is increase. So these are the diseases that we can do. It is for diagnosis. Okay. Next,
So why
import.
is HCT more in, there's difference between male and female?
It depends on the amount of, I mean, blood present in the body. So normally male they have more liters, and female they have less.
Okay.
Yeah.
Okay. Sir.
Okay. Does anyone know what is apheresis? Hello. Just keep guessing. We can have the guessing one. What is meant by apheresis? It is similar to fractionation. Fractionation, I think someone mentioned. It is similar to that. But what is apheresis? I think Vinu sir mentioned, no? Fractionation.
Anything related to like plasma, red blood cells?
Yeah, so fractionation we meant it is a separation of components, right? Apheresis is a device or a yeah, it's a device that separates these items. Here they mentioned the process of apheresis involves removal of whole blood from a patient or donor within an instrument that is essentially designed as a centrifuge in order to separate blood components. So it is like there will be one device, will be connecting our donor or patient to that device. So that device will automatically takes the blood from the donor and it will separate the components and it will give the remaining back to the donor. So that system is called apheresis or apheresis system. So there are like two types. One is like therapeutic apheresis, one is normal donation. Normal donation is like if you go blood bank, they'll just take the blood and they will transfuse the blood later. If it is a therapeutic apheresis, what's the case is like there will be one device. On one side we have donor and one side we have the patient. So we'll be taking required component from the donor and we'll be giving it directly to the patient. So that connection is called therapeutic apheresis. This concept is clear now because my project depends on this topic only. So if you have any questions, yeah, you can shoot it out.
Shivanidhi,
Yes.
um, as you said, separations of plasma, whatever all the components that is being present in the blood,
Okay.
which can be transfused to the donor as well as the patient, right? Is
Yeah.
there
So
any
mm,
possibilities of sending any particular component to the donor, sorry, to the patient? Like if the patient is not having a good plasma level, this
hmm.
particular plasma can be transfused to the patient.
Yes, I think you
Is
make
that
my work
possible?
simple. So this is my project.
Hmm.
I'll explain you in detail. I mean, in further slides or in the further video I have, will show that.
Okay.
Sir, whether apheresis is expensive?
Yeah, means in our Indian rupee, it is almost 26 lakhs. The device setup. I mean, we have a device over here. Means in our ODC, but the actual price is like around 26 to 27 lakhs. So there are different types of apheresis. One is normally automated blood collection system. Another one is a blood processing system. If it is a only processing system, then it is 1 crore. That device also we have in our lab. And the other one is apheresis system. We have separate apheresis system. That device do collection, depletion, and exchange means transfusion. All these three that will do it is around 40 lakhs. So these are the like our Indian rupee, it's the estimation for these devices.
Okay.
Yeah. Any other questions on apheresis system?
Similarly,
Yes sir.
after separations of the components,
Okay.
how long it can be stored and it can be transfused to the uh, donor to the patient.
So it depends on the component. For RBC, I think the lifespan is like 10 to 12 days. And for plasma, it is around 3 4 days, I believe. Plasma or platelet, it is 3 4 days. Uh, and for other component, platelet, yeah, it is similar, 1 to 2 days.
How much
So
quantity that can be stored at a time
no,
in
it
terms
is not depends on the quantity. It depends on the lifespan only.
of, okay.
Huh.
So is there any specific groups as that is blood group as contain more number of lifespan,
No, no, no,
time limit.
no, no. Here, if you can see, na, in apheresis in the medical field, they have certain range only. So even though we have more number of platelets or our body, like we are like obese, so we have more blood, we can't donate more than the assigned range. So it's from the FDA approval, approval from the, it's like legal approval is there, so we should take only 1.5 yield minimum to a 4 yield of platelet only. Like that, we have defined range. We should not take more than the defined range, even though the
No, no,
patient
no,
is
no.
having more.
No, 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 no. My question is,
Mm,
if you have different blood group components like O positive, B positive, B negative, A and B
mm,
negative, is
okay.
there any you are separating? See, for example, I am O positive candidate, right?
Hmm.
I am suppose I am donating the blood, right? In
Mm,
that, you have some content components like plasma, WBC, RBC,
hmm.
so and so, right?
Yes.
When comparing to the other sorts of blood groups, is
Mm,
there any special, like for example, A1B negative, A1B positive is rare blood group, right?
correct.
Is there any advantages over on this to that, like that I'm asking?
No, there is no advantage. So in my project, so we have all these blood groups. So here we don't have any specific A1 B positive like that. So we have only O plus O negative, B plus B negative, AB plus AB negative, like this only. So maybe I'm aware of. I mean, I'm not aware of. In my project, we don't have any specific that okay, this blood group is like superior, so we can have more components like that. We don't have.
No. Okay,
No.
okay.
Any other questions? Okay, then yeah, we can. Yeah, I think someone have question.
We'll keep the discussion at the last, I guess. You can complete Sivnidhi.
Yeah, okay. Okay, sir. Okay, the next one is like principle behind this apheresis system. So like I mentioned, so we'll be connecting our donor to the device. So this just a principle that I'm going to explain. So we are connecting donor, and from donor we are collecting the blood. So here I mentioned anticoagulant. So if we take blood out from our body, within 5 to 10 minutes it leads to clottage. Okay, it leads to blood clot. So in order to prevent that, we'll be having adding the anticoagulant. So if we add anticoagulant to our blood now, we call it as, in our term, in my R&D term, we call it as whole blood. A blood with AC, we call it as whole blood. Then the whole blood goes to some certain tubing set. Tubing set means one container. I'll show you that container later, tubing set. And so now blood gone to the container. So from that, we need to give the blood to centrifuge. So we all know that with the help of centrifugation only, we'll be able to separate the blood components. So from the container to the centrifuge, with the help of pumps, we'll be diverting that blood from container to the centrifuge, and in centrifuge, centrifugation will happen. So centrifuge will rotate around 3000 rpm, rotation per minute, to separate the blood components like RBC, buffy coat, and the plasma. After that, whatever components I required, for example, the patient he needs only plasma, so I'll take only plasma. I'll give the remaining components back to the donor only. So it's a simple. It's the principle and the flow. How we separate blood, how we separating the constituents, and how we give it back to the donor and the patient. Okay, now I'll tell you what main components we required in the apheresis system. So if you consider any device, so these are the things. So here in the flowchart I mentioned pumps, centrifuge I mentioned. So there are a few more main components that are required to do this entire process automatically. So first one is pump. So I mentioned first one I mentioned here pump, AC pump, because first we need to mix AC to our blood. So in order to mix, we need a separate AC pump to mix that AC to the blood. Then we have inlet meaning we are taking, return meaning we are giving it back to the donor, and plasma platelet, and there will be RBC pump also. So for the different components, plasma, platelet, RBC, we required separate pumps. These pumps are just to pumping things from one place to another place. Then we have walls. Here walls meaning it just block. So for example, now I am collecting only RBC. So after RBC collection, I need to close that bag. If I'm not closing, otherwise, if I'm not closing, then the RBC again flow back to the container. So I don't want that. So we have main components walls. So wall will block the collected components back to the container. So we have RBC wall, plasma wall, and the platelet wall, and we have sensors. Sensor is to sense the pressure inside the tubings. So the blood flows inside the tubes. So we need to find access pressure sensor. Here access meaning how mean what is the pressure if we are taking blood. So that is inlet pressure sensor and the return blood pressure sensor. So access meaning it covers both in and out, inlet and the return. And we have centrifuge. We need to constantly monitor the centrifuge pressure, and up level and lower upper level and the lower level. I'll explain you later. And we have detectors. So detectors is to check whether the AC is flowing or not. I mean, AC is adding it to the donor's blood or not. If it is not adding, then it may leads to risk. It will clot the blood. Then our entire procedure will be at vain. Then we have RBC detector. RBC detector is like after centrifugation, we are collecting components, right? We are after from the centrifugation, we are taking out the components. Plasma we are taking, then we are taking buffy coat, then RBC. When we are taking buffy coat, if the RBC is added or mixed, then it is waste. So in order to detect that, we have RBC detector and we have leak detector. For example, during the procedure, if my tube got burst, so the blood or the fluid it got spread or spilled inside the centrifuge, then to detect in order to detect that, we have leak detector. Yeah, I think now we can see the real example. Till now you have any questions? Then I think next I have only two videos to show, and from the two videos I can explain you. You have any other questions? Anyone? Okay, then I think we can see the video. I think my uh, Chrome screen is visible, right?
Yes, visible.
Okay.
Can all the participants see the video?
Yes, ma'am.
Yes, ma'am.
Okay, thanks for confirming. Just see the video. I think audio is not important. I'll just pause the video and I'll explain you. See, here I mentioned the blood from the patient is mixed with anticoagulant fluid. So here I mentioned we are taking blood from the donor and we are adding AC. So this process this blood we call it as whole blood. So now we are sending this whole blood to the centrifuge. So this is called centrifuge. Is my mouse is also visible, right? The mouse pointer.
Yes,
Yes, sir.
Yes,
visible.
yes.
Ah,
Visible.
okay, okay, okay. So now the flow will be clear for you all. Okay, so now blood we are taking and AC we are adding, so it will be called whole blood. So whole blood we are giving it to the centrifuge. So here that centrifugation will happen. Blood and AC enter the centrifuge. It rotates around 3000 rpm. See, inside the centrifuge channel, blood is separated by specific gravity using centrifugal force. As rightly mentioned, because based on the density, the components will like deposited. Like first one is RBC at the bottom, platelet and the white blood cells we call Buffy coat, and top plasma. See, here you can see after separation, there are two lines. One is red, one is yellow. Yellow is the required component. For example, I'm going to collect plasma only. Do you all know what is convalescent plasma therapy? During COVID, this therapy was like helped
Adding
a lot.
blood who our blood count is less.
Mm, not exactly. There are like nearby meaning.
Okay.
Convalescent plasma therapy, see, in COVID times, na, like whoever recovered from the COVID, they are volunteered to give the plasma. So this convalescent plasma therapy is like the person who recovered from COVID, we are taking their plasma and we are giving it to the COVID patient, and we are removing their means deceased plasma. Okay, in that, if we do this, na, the patient he'll get more immune to recover from the COVID. So that was the therapy which got viral during that time. Like it got famous, we can say. So our product also helped to in 2021. Our product we have released one short one to uh, reduce the time of collecting plasma. So that helped, and we got recognition also. So this is that process only. See, here we have separated the plasma, this yellow line, and the remaining component we are giving it back to the patient or donor. See, here it is showing we are separating the plasma. Consider this patient, he's a COVID patient. Okay. So from here we are collecting, we are removing his deceased plasma. That is called waste bag. Here we are collecting his deceased plasma, and this yellow bag is right. So this is the person who recovered from COVID. We have taken already plasma. So that plasma we are injecting it to him. Okay, from his blood. So we have withdrawn his blood. We have removed his deceased plasma, and we are adding now recovered plasma, the recovered or healthy plasma to this patient. This you understood, right? What I'm trying to explain.
Yes, yes, even.
Okay. A replacement bag or replacement fluid is the same. We are replacing the deceased plasma with the healthy plasma. That's it. Any questions here? I'll show the real blood video.
Similar, this treatment is basically only for whose plasma count is less or immunity is less. Only they can use this, or even hemoglobin less patients also can use this type of treatment.
Yeah, so we can use, so hemoglobin less people we can't donate blood, so they can get the blood, right? So
Okay.
donor, we have many protocols. So if we help explain it, it is a bigger topic. So we have many protocols. So in this same device only. So this is that
Or the same
apheresis.
device can be used.
Yeah, same device. We have different this cassette. I mentioned a tubing set.
Okay, okay,
So this tubing set, and we need to do some configuration in the GUI.
okay,
So it's like more technical. So that's why I just covered it only generic way.
okay, okay, sir.
Yeah. Okay. If no questions, then I can play this realistic, mean real example video. Okay, I think no questions. I'll play this one.
Used to perform various therapeutic apheresis cell collection and processing procedures. In this video, we will review the mononuclear cell collection, or MNC collection procedure. The operator, such as a nurse or other clinician, begins by loading a tubing set onto the device and connecting that tubing set to the patient.
See, the first important thing is like whoever it is. For example, if the giver giver is a donor, not a patient. If it is a donor, then we need to configure their vital details, donor vital details. So here it is a gender, we need to mention male, female, then height, what is the weight, and what is the HCT value, what is the flow rate, that we need to set. So she is called operator, so operator will be there, and she will configure things, donor vital details, before donating the blood. So here the calculation will happen. So calculation, as output of the calculation is like we get to know what's the total blood volume, TBV. We call it as TBV, total blood volume. So from this donor, how much blood we can take and process. That calculation it will do, that will be part of TBV. So for example, the minimum TBV is like 4 liter we can process from the healthy donor. So if I'm going to donate, then with my vital details, it will be around 4800 ml. It means 4.8 liters. So I can take, they can take 4.8 liters of my blood, and they can process. They can do separate the components, and they can use it. So that's why this is important, the configuration part.
Either through an arm vein or through a central line. After the operator enters some patient information, including cell counts, the system begins to draw the patient's blood. Blood is
See, here you can see our system. This we call it as tubing set. This white color one, no? So this is a tubing set. It has two ways. One to connect AC. So here this orange color and this black color one is called detector. This is AC detector. So for example, now I'm connecting AC, but I didn't open the clamp. Meaning I'm not opening that AC tube or something. If I'm not opening it, then the AC won't be mixing with the patient blood. So that is the risk. So in order to prevent that, we have this AC detector here to detect the flow. So here we have backside, we have the AC bag, and we have connected, and this detector will detect the fluid is passing or not. If it is passing, if it is not passing, it will raise an alarm. Alarm mean it will notify the operator with the sound and the light. And this tube, na, this tube, we have two tubes, one for inlet, one for the return. So this orange color and green color, this orange color is to take a blood from the donor. So he's a donor. So we are taking his blood, and we are giving it to the tubing set.
continuously pumped through the tubing set and back to the patient during the procedure. The system cycles through several accumulation and collection phases during the procedure. During each accumulation phase, the chamber fills.
I've mentioned you pumps and the valves, right? The main components. So we call these as pumps, rotor. Okay. So these are the each pump, they have their own functions. So this we call it as AC pump. So this is responsible to deliver AC from the back to the centrifuge. Okay, and this one is like inlet. So if this rotates, na, it means it is taking blood from the donor, and it is giving it to the centrifuge. This pump. And this one is like plasma collection pump, and this one platelet collection pump. And here we have one ba- uh, big pump, so that is for return. So once we're done with the collection of required component, that is responsible to deliver the remaining components to donor. Okay, so this is about pump. And I mentioned valves. So these are called valves. This is called RBC valve, and this is for plasma, this is for platelet. So now you can see there are two tubes in between the valves, right? So one is like processing, one is like collecting. So once the centrifuge separated the component, first it will take the If I'm collecting it, I just want to block this tube. Otherwise, due to the gravity, the collected will again go back to the container. Na? So in order to prevent that, we have this valve. Once we collected, the valve will close that tube. So it won't let the RBC or plasma or platelets to fall back again to container. Understood?
It will get reverse flow will be blocked. That is what you're saying, sir.
Yeah, the
No
collected
reverse
one,
flow will not be done.
yeah, reverse flow. It won't happen.
Okay.
With cells. When the chamber is full, the system triggers a collection phase and pumps the
Here you can see where this pump is rotating, right?
accumulation cells.
You can see this is rotating and this is rotating. It means it is collecting blood and it is adding AC to it. So the blood with AC, it is now coming into this cassette, and from the cassette, it is going to centrifuge. Now you can
Into
see.
the collection bag. The number of times the chamber is filled throughout the run depends on the patient's
See, now you've seen this flow, no? So it is going. So this tube, na, this tube is called a centrifuge tube. So now this is going inside the centrifuge. You can see the
The
path.
number of times the chamber is filled throughout the run depends on the patient's mononuclear cell count, goals of the procedure, and events that occur during the procedure. The patient's blood is continuously pumped through the tubing set. The inlet pump draws the anticoagulated whole blood through the inlet line into the channel. As the blood moves through the
Here you can see inside. So we can't open and see if the centrifuge is rotating around 3000 RPM. So what now in the device we have camera, or we have open space, and we have optical resolution we have, and we have camera also to see what is actually happening inside. So this you can see we are collecting inlet blood. No, the inlet blood is collecting here.
channel, it begins to separate into three layers: red blood cells, buffy coat, and
See, it is
plasma.
like centrifuge is
The
rotating, but
red
we can
blood
able to
cells
see
are
the image
contained:
properly.
red blood cells, buffy coat, and plasma. The red blood cells are continuously returned to the reservoir and pumped back to the patient. The collect pump pumps the buffy coat, which contains the target cells, from the channel and into the chamber. The platelets are separated from the
Hmm. This is the important one. Um, yeah, I mentioned that we can collect RBC, plasma, and platelet. We won't be collecting WBC because WBC, it depends on individual's immune system. Okay, so we can't transfer immune system to one person to other person. We can either deplete the WBC, but we can't exchange the WBC, or we can't transfuse the WBC. Okay, so this is the important one, which separates buffy coat, I mean the platelet and WBC into the platelet. For example, this cone is called leukoreduction cone. Leukoreduction mean it removes it removes WBC and gives only plasma. So this is a big topic, so I'm not going to explain it fully. Just you can see this cone will separate our buffy coat, platelet and plasma, into only platelets. The WBC will deposit in this cone only. It won't transfuse to the bag.
target cells in the chamber during a secondary separation step. The platelets are then pumped back to the patient. The system detects when the chamber is full of target cells and automatically moves into the collection phase. In the collection phase, these cells are pumped to the collection bag. The way collection phases are triggered can be tailored to the patient or procedure goals. After the cells have been flushed from the chamber, the system begins refilling the chamber. The system repeats these phases until the run target is achieved. The spec
Okay, the flow she shown right now, that is like from the centrifuge after collection, after separation, and the flow is like we have separate tubes here, so it will take the component from the centrifuge and it goes here with the help of pump. It goes to the collection bag. So we have separate collection bag, so it goes to collection bag.
the chamber. The system repeats these phases until the run target is achieved. The Spectra Optia's automated interface.
Okay, so these are like for different protocols. I don't want to confuse you all. Okay, so this one I told you, right? If we have something, for example, AC is not passing through the detector, so we will get a sound, beep sound with this red light, and the screen will be like this. It will show the status line, like red color status line. It will show what has happened. In this case, it is like someone pressed the pause button or the operator pressed the pause button. So it is showing like this. So it's a safety alarm. So safety is very important here.
System that allows operators to easily troubleshoot and optimize procedures. If the system detects an operation error or a potentially unsafe operating condition, it triggers an alarm. The alarm screen shows all the possible causes of the alarm. The system may stop the pumps or the centrifuge. The operators can customize each procedure performed by entering run targets.
This is
The
again
system
different thing.
to 100% blood remaining in the set, back the blood remaining in the set to the patient. The Spectra Optia stores procedure data reports for up to 100.
Here they are saying we can see, here we can see the report, run report. So the whatever the run we performed, we call it as run. So whatever the test run we performed, we can see the report from the GUI itself. And we have one thing called rinse back. For example, in the cassette, there may be some residuals will be there, blood residuals will be there. To remove that residual, either we can use our collected plasma, we collect extra plasma to do the rinse back and flush it. I mean, flush. To remove that residual, we do call flush or rinse back. So we do that process to remove the remaining residuals and given back to the donor or to the patient. So that's why we call it as one term, rinse back. This is my client, so I can't expose, but it's okay. Okay, any questions? I think you all are active, right?
Sivanidhi,
Hello. Ah, sir.
I have a question for you.
Okay.
Not for you, it's a general question.
Hmm.
Suppose a patient undergoing COVID positive, right?
Okay.
Okay.
Hmm.
Um, from COVID positive patient, we are taking the blood. Okay. We are taking the blood, and from other donors, we are transfusing the blood. Okay.
No, I mean, you mean you're a COVID. Mean, for example, we have one COVID
I
patient.
am
He's
not the
take
COVID patient.
not you,
Hmm?
not you. I mean, for example, someone is there.
Hmm.
Uh, I mean, that COVID patient is taking blood or he's
No,
donating
no,
blood
no, we are taking the blood out
from him. Blood.
from
Okay.
him, from
Hmm.
from the patient. Okay,
Okay. Hmm.
from the patient. Then we are transfusing the blood from the donor to the COVID patient. Like what you said, the COVID positive patient was recovered. Okay,
Hmm.
okay. We are transfusing the blood to the patient, donor to the patient, right? Now, the blood which has been taken from the patient,
Hmm.
whether we can able to separate uh, the good plasmas which is present in the COVID patient.
No, that is not possible. So it just will be just able to separate the components. It won't show like healthy or bad. So with the help of blood test, so before donating or before transfusing, we'll be taking that CBC test. I
Hmm.
think we all at least one time we have taken CBC test, right? So it will show all the things. So it
Hmm.
will clearly show the plasma is healthy or platelet is healthy or RBC restricted. It will
Hmm.
show there.
Okay.
Okay, so
Because
we can't donate. Huh.
my question is,
Hmm.
when it comes to zero level, sorry, when it reaches to the minimum threshold level only, will the indication will shows that our blood transfusions cannot be done and blood cannot be donated to the others, right? That
Hmm.
is what my question. You have made it clear.
Yes. So first it will check the it is within the normal range or not. Okay. Then it goes to now everyone is checking COVID positive negative. If you are definitely COVID positive patient, we can't take blood from you and process. Only if it is a convalescent plasma therapy, we remove your diseased plasma and we'll replace it with the good plasma. That's it.
Okay. And one more question from my side.
Okay.
The thing is, you said that buffering, the
Buffy code,
plasma cone,
Buffy
buffy
code,
cone.
platelet and WBC. Huh.
Uh, from research
Mm-hmm.
related work, how this buffy code will work out? Is there any research possibilities? Is there for the researchers researching ideas and methodologies, innovations can be generated from that but particular buffy code?
Mm,
New innovation ideas can be generated from your side. Since you are into this project,
okay.
you were talking about plasma and RBCs and less, and there is no weightage at all for buffy code, right?
Correct.
Okay. If, from researcher side, as we are from the faculty side, we used to think about what kind of research from that particular thing can be see, because in plasma there are so many researches, RBCs there are so many researches. In Buffy code alone, is there any possibilities? If there is any possibilities can be carried out in future, what is your suggestion so that
I
we
think,
can move
see, I think Buffy code related researches were already done. That's why they have designed this specific cone shaped this chamber, right? Otherwise, there can be anything. See, this is my another device. There are like two device we have blood collection system and one is apheresis system. So this is my one of the other project. Here you can see the shape is similar to what the other device had. Okay.
on?
Anyway, the both process is like deposition only. The main principle behind this is deposition only. So I think researchers, it may be done. We can check actually.
Okay, we will discuss later.
Yeah. Okay.
Sir, excuse me, sir. I have one doubt.
Okay.
Sir, can you hear
To
my voice, sir? Is it audible? Yes?
to me, right? Your voice is audible.
Sir, my name is Shankar,
Okay.
and this one, in what time, how much time it will take to suck the blood from the donor? How much time it's required to store the blood into the bank, sir, from your system?
See, from the
Can you,
banks, it
uh,
depends on the components. For example, RBC, as I mentioned earlier, we
uh,
can store it for like 10 days, maximum 10
no,
days.
no,
I don't know the
no.
exact days, but
How
it's a
much
10.
time are required to take the blood from the donors?
How
How
much
much
time you required? Okay. See, if it is a platelet, then it goes to that LRS chamber stuffs. So it will take around, for a minimum yield, it will take 20-30 minutes. If it is a plasma is the topmost component, right? So for 100 ml or 200 ml, we can donate it in within, mean separate and we can store it in within 10 minutes. Okay, if it is RBC, still same because RBC, what we need to do, it is a dense one, so it is at the bottom. So first we need to send the plasma back to the donor, Buffy code back to the donor, then we need to collect RBC. So it will take 20 minutes for 100 ml.
what will be the temperature maintained, sir, inside the chamber?
That exact temperature, I don't have in my mind. I mean, I need to check. But
Oh,
I'll give this answer to Satish sir. You can take from him.
oh, okay, sir. Thank you, sir.
Yeah. Okay. Any questions?
Actually, Sivani, your video point of presentation is much impressive, which shows actually for myself a good dimension. Only doubt, maybe a
Mm-hmm.
little doubt also.
Mm-hmm.
You addressed on that COVID scenario, right? Uh,
Convalescent plasma therapy.
yes.
Yes.
Is it something like transferring of the antibodies to the receptor?
Uh, Not exactly. See, I mean, there will be some time frames will be there. So the patient will, I mean, the recovered patient, the recovered guy, he'll be like isolated for number of days. Then once all his results are like positive, like multiple times his results are positive, then only we'll be taking his healthy plasma. Okay.
Okay.
So
Okay.
we'll be having some time frame, some isolation period we say. So after the isolation period only we'll be taking his plasma. So here just to generalize things, I'm just taken this example,
Okay.
but
Okay.
there will be a lot of medical uh, things also gone through. So here we are in the R&D. So
Uh,
we only work on this one. So here also in my lab we are not using the real blood. So we are using NaCl.
uh-huh.
So NaCl, they are calling it as 99% the blood composition, means similar to 99% of the blood composition. So we'll
Mm.
be using that. So in my Lakewood team, sorry, US team, they are testing it with the real blood, testing with bovine blood, not human
Mm.
blood.
Okay. Uh-huh.
So
Uh,
our readings will be like somewhat similar. 99% will be similar, but the final decisions will be made by them only, because
uh-huh.
here we don't have the license.
Right. Right. Right.
Uh,
Okay. Okay, Shivniti. Thank you.
yeah, okay, sir. Any other questions?
Sir, what
Participants.
is the cost? What is how much the cost of the equipment, sir?
Yeah, so the basic one, only automation collection system, it is around 26 lakhs. If it is an Apheresis system, around 40 lakhs. If it is a processing system, it is 1 crore. See, processing system, why it is costly, I'll explain you. Here in this Apheresis system and the blood collection system, our donor should be connected lively throughout the procedure. Until I take the component, I'll send back to the remaining components to him. He should be actively available near to the device. One operator should be there, but in the automated process system it's like our normal process. Now I can go somewhere, I can donate the blood, so it will be like whole blood. We are not separating anything, right? So we are not separating it into the components. This processing system, what it will do now, we can have four chambers, so we can have four donors blood inside it, and we can, with the help of centrifuge, we can separate the components. So it will save, it saves time. So in order of taking one donor's time, the processing system is taking four. It is processing four donors' blood. Correct. That's why it is very expensive.
At a time, four donors can be give their donate their blood. Okay, sir. From the
Uh,
four
I mean, not at a time. So we can process that donated blood at a time.
at a
I
time.
can
Okay.
show you if I have that device image here.
Or, it's available manufacture from India, sir.
No, sorry, it's not manufacturing in India. It's actually it's a Europe-based company, and we have more clients from US, and we have devices in India. I mean, you can see in Gujarat also we have devices, and some of the blood centers. The same device we
Any
are working on, right? Sorry, can you
any further R&D related issues are there, sir, in that equipment?
R&D related? See, it again comes to us only. So we are working in R&D, right? So what things will be like in some region, for example, Japan, that region during winters, the testing, this tubing set, na, I mentioned cassette, they'll become frozen. Okay, during their winters, it became like frozen. So they said they want some cooling period, or they want some heat time, or he want more temperature. That minor changes they expect from R&D team. That is from us. Okay, but research or project perspective, I need to think of.
Okay, sir. Okay, sir.
Okay,
Okay, sir.
so
Thank you
this
very
is
much.
that one. This is that one blood processing system. Here you can wait if I have the video. Revolutionary. Uh, Satish, so I can play this video. It
Yeah,
just
yeah,
it
please.
is showing 8 minute. It will be so this one. Uh, this one is like a four. We call it as bucket. In this device, we have bucket. So here we can keep our whole blood inside, and it same rotates 3000 rpm, and it will separate the components. It is like no need of any donor connection, live donor connection to this device. It just once we collected the blood from him, we need to just agitate, then we need to place it here. That's it. See, as I mentioned, so they have blood bag along with the collect bag. See, this is a whole blood bag, and this is a collect bag. So after the separation happened in this bag, with the help of these valves and the flows, it goes to the separate bags. So platelet bag, plasma bag, and the RBC bag. So what happens now? This actually saves time. It is doing four blood units separation. Our device do only one patient separation at the time. So that is the difference. And here it is a manual thing, and that is a automated part. See, now it's separated into separate components. See, this resources now you will find it in Google itself, so you can search for my client, and you will get all the products. If you genuinely want to do your research in the blood domain, then you can search. So they are the leader. Till now, they are the leader, global leader in the blood and cell technologies. So you can visit their site. Any other questions? Yeah, I think we have only 1 minute left.
Participants, any questions, or else we will wind up.
Still, if you have any questions now, you can reach out to Satish sir, so he'll send me. Sir, you send me the questions if they have
Sure.
reached out to you.
Fine,
Okay.
fine. Okay, Shivani. Uh, Participants, shall we wind up? Neela ma'am,
Yes, sir. Yes, sir. Study session.
ma'am, we'll wind up, ma'am.
Okay.
Okay, then
So thanks.
it's nice meeting you all.
Yes, thank you,
Shivani,
sir.
thank you.
Yes, yes, sir. Thank you. Welcome.
Shivaji, thank you.
Thank you, sir. Thanks for joining. Yeah.
Good presentation.
So thanks, Sunidhi, for
Thank you, sir. Mani sir is also there. Nice. Thank you.
Happy to see you with a good presentation, Shivani, actually.
Yes.
Seriously, I'm also happy, sir. I
Uh,
seen my gurus here, all three gurus.
Really a good lecture, actually. Never been like for the past 1 hour, it was like a good discussions.
Thank you, sir. Thank you. Okay. Thanks, everyone. Bye bye.
okay, thank you, Sunidhi, for the lecture and accepting our invitation for the executive.
Thanks, ma'am. Yeah. Welcome.
Thank you, sir.
Thanks all the
Thank you. Bye bye.
participants also for being interactive, for the video content and for explaining in detail for us.
Madam,
So thank
Madam,
you
good
all.
evening. Madam, good evening. Can you put
Good
the
evening, sir.
feedback link in the WhatsApp group, ma'am? Can I have it?
Yes, sir, I'll put a feedback link now.
Yeah, thank you.
Okay, sir. So thank you all the participants and Sunidhi.
Thank you, ma'am.